Good morning, all. We will start the session. So we were discussing the characteristics of bipolar logic. In the last session, we have seen what are the logic levels and what are the DC noise margins of bipolar logic. In bipolar logic, the most widely or the most commonly used logic family is TTL logic family. So when we say the bipolar logic characteristics, so obviously it refers to the transistor logic characteristics. So we will continue the TTL logic characteristics. So what are the logic levels of a TTL logic family or the bipolar logic family? So in TTL logic family, the logic 1 and the logic 0 are represented with a range of voltages. The logic 0 is represented with a range of voltages between the 0 to 0.8 volts, and the logic 1 is represented with the between the voltages 2 to 5. And coming to the DC noise margin levels, the DC noise margin levels. So with respect to the given voltage levels, so the high state noise margin level and the low state noise margin levels are determined that. So the high state logic noise margin is 0.7 volt, and where the low state DC noise margin is 0.3. So that you can observe in TTL logic family, the noise margin levels are very low. Therefore, they are highly susceptible for noises. And the second and the next characteristic is the fan out. We know what is a fan out of a digital gate. We know what is the fan out of a digital gate. So what is a fan out? The fan out is a measure of the gate, that the number of gate inputs that are connected to the single gate output, so that the single gate output can drive that number of the gate inputs here. So the fan out is the measure of the gate, that the number of gates that are driven by the single gate output. That is, it is the ability of the circuit, that the maximum number of the gates that can handle by the corresponding gate. But if you see in CMOS logic family, is the DC fan out of CMOS gates is a high value or low value? So if you see the DC fan out in CMOS logic, is the DC fan out is a high value or low value? Obviously, the DC fan out in CMOS logic is high and very high here. So that is the DC fan out of the CMOS outputs driving the CMOS input is very high and high. So almost we can say that it is a virtually unlimited here. The DC fan out of the CMOS outputs driving the CMOS inputs is virtually unlimited. It is because the CMOS inputs require a very low amount of current. It requires a very low amount of current, say almost zero current, which means that it is not zero current, but it takes a very low amount of currents in either of the high state and the low state here. So that's why when a CMOS output is driving the other CMOS inputs, the DC fan out is very high or high, or you cannot say that virtually unlimited. Virtually unlimited here. Virtually unlimited. ఎవరైనా హ్యాండ్స్ రైస్ చేస్తుంటే కనుక అది ఒకసారి మీ ఆప్షన్స్ లోంచి తీసేసేయండి, because some unwanted text box is appearing on the screen. It is because of someone is raising their hands. So if anybody if anyone is done that one, so just please remove that one. So here the DC fan out of the CMOS outputs driving the CMOS input is virtually unlimited. So the fan out, you can see that the fan out of the CMOS gate, you can see that from the in terms of hundreds to the thousands here. A CMOS gate can drive the hundreds of the CMOS inputs, or a CMOS output can drive the thousands of the CMOS inputs here. So that's why I'm saying that it is the virtually it is unlimited, which means that the DC fan out of a CMOS gates is very high or high. We will see an example in next upcoming slides. So it is because of the CMOS inputs required almost no current in either of the high and low state. So on the other hand, if you see, what is the fan out? What is the DC fan out of a TTL output driving the TTL inputs, or a CMOS output driving the TTL inputs? In such cases, the DC fan out is low, or you can say that it is very low. So which is a very limited number of gate inputs. So here you can see the two conditions: the CMOS output driving the CMOS inputs, the CMOS outputs driving the TTL inputs, or the TTL outputs driving the TTL inputs. So in the first case, the CMOS, if the CMOS is driving the CMOS, so the fan out is very high, so that you can connect more number of CMOS inputs to that gate output. But it is not the case like in the TTL. So if a TTL gate is driving the another TTL inputs, so it cannot drive more than a limited number here. More than a limited number. So the DC fan out of the TTL or the CMOS outputs driving the TTL inputs is very low, or you can say that it is low. So it is because of the TTL inputs draws the significant amount of current in the high state and low state. Especially in the low state, the TTL inputs, they draws the a significant of the current here. So because of that, the fan out will be reduced when a TTL output drives the TTL inputs, or the CMOS outputs driving the TTL inputs here. Then how do we measure the DC fan out of a particular logic here? Say we are in the TTL logic family. So now if we wanted to determine, or if we wanted to measure the DC fan out of a TTL gate, then how do we measure the DC fan out of a TTL gate? So here the fan out, it depends on the TTL inputs. The fan out, it depends on the TTL inputs. So with respect to the high state and low state of the currents. So here the currents required by the TTL input is depends on whether the input is high or low, specified by the current parameters here. There are two current parameters, IIL maximum, IIH maximum. So these two are the currents. So one is the IIL maximum current that an input requires to pull it low here. And the IIH maximum is the maximum current that an input requires to pull it high. So what is the maximum current to pull the input to the logic 1 state, and what is the maximum current that at an input it requires to pull the input to the logic 0 state. So IIL maximum is to low value, H maximum is to pull it to the high values here. So here these two current parameters, along with these two parameters, we have the other two current parameters. We have the other two current parameters. We have the other two parameters, IOL maximum, IOH maximum here. And here also you will see that the IOL maximum is the maximum current an output can sink in low state, and the IOH maximum is the maximum current an output can source in the high state here. So how to understand these four current parameters here? So to understand these four current parameters with respect to a DC fan out, so we will try to understand what is a source current and what is a sinking current. What is sinking current and what is sourcing current. So for this, we will consider the two cases. The first case, when a TTL input is driven low by the output of the another TTL gate. So take the two gates here. You can see you are not able to see in the complete two stages of the TTL gates here. So in the first part, we have the first TTL gate output stage you are seeing, and in the second TTL gate you are seeing the input stage and the phase splitter state. Okay, so now the condition is when the TTL input, so this one, the second one, when the TTL input is driven by the low output of the another TTL gate here. Low output of the another TTL gate. So in this case, if you see, so here the output is 0. And so here the first stage gate is the driving gate and the second stage gate is the driven gate. So because the second gate is driven by the first gate and the first gate is driving the second gate. So so here we are considering the low state here. So the output of the first stage is the low. So when the TTL input is driven by the low output of the another TTL gate, in this condition if you see, the transistor Q5 is on, thereby it provides a path, ground path, thereby it provides a ground for current flowing out of the diode D1XB here. See, here you have a current direction flow here, because in the first gate, the output at the first gate is 0. So this 0, it makes the D1XB diode to forward bias. So when the D1XB it is forward biased, the current flows from the VCC to R1B through to D1XB to see this one, D1XB2, and through the output of the gate to the ground here. So which means that the current flowing into the output of the transistor or the output of the TTL gate 1, and this is TTL gate 2. So in this case, if you see here, the current is flowing into the transistor. The current is flowing into the transistor output. So when the current flows into the TTL output in low state, then the current is said to be the sinking current. So which means that the current flows into the output of the circuit, resulting that it is pulling down the output voltage to the logic 0 state. Logic 0 state. In the similar case, you can take for the sourcing current. So in the sourcing current, the TTL input is driven by the high output of the another TTL gate. So now the output at the TTL gate is 1, and this one is driving the second TTL gate here. So if it is the case, now the current is flowing out of the gate output here. Now see, the current is flowing out of the gate and which is entering into the second TTL gate here. But since the output of the TTL1 is at logic high state, and this is connected to the D1XB to the cathode terminal. So this high state voltage causes the D1XB diode to reverse bias here. We know what happens when a diode is reverse biased. When diode is reverse biased, it is said to be in off state, and ideally there will not be any current flowing in the diode, but practically there will be a leakage current flowing in the circuit. So that leakage current will be in the order of the microamperes here. So when the output at high state, it causes the D1XP of the TTL gate 2 is reverse bias. Therefore, there will not be, ideally there will not be any current flowing, but there will be a leakage current flowing into the D1XB diode. So now see, now the current is flowing, now the current is flowing. So now the current is flowing out of the output. The current is flowing out of the gate. It is flowing out of the gate here. So this current is called source current because the output can source to the high state value and which is entering into the second gate input. And if you see the sinking current, in the sinking current, what is happening? The output is at logic 0. Therefore, this logic output makes the D1XB diode to forward bias. So, with respect to the TT2 gate, with respect to the second gate input, the current is going away from the circuit, and with respect to the TT1 gate, the current is entering into the output of the TTL gate 1. So the current flows into the output. See the word, the current flows into the output of the gate. That current is said to be the sinking current, which causes the output to 0. So why I am stressing on these two is the sinking current and the sourcing current. Whatever the parameters we have stated here, the IIL maximum, IIH maximum, and IOL and IOX. These four parameters can be easily understood from the sourcing current and sinking current concept here. So now we will see the IIL maximum here. So what is the case here, IIL maximum? So IIL maximum, if you see, when the TTL output, so this one, see, when the TTL output is in low state, so now in this state, the current is flowing out of the TTL input. So again, we can move to the circuits here. Just so now see here, IIL maximum, IIL maximum here. So when we can see this parameter IIL maximum, so when the output of the TTL gate is low, when the output is in low state, so the current flows out of the TTL input. Now the TTL input is the second stage input. The current flows out of the TTL input and it enters into the TTL output. It enters into the TTL output here. So that current is called IIL maximum. That current is called IIL maximum. See, what is the maximum current that you can see in this condition? You see, is the diode is forward bias or the reverse bias? The diode is forward biased because of the low voltage. So when the diode is forward biased, obviously the current will be in terms of the milliamperes only, but it is flowing out of the input circuit, therefore it will be negative current here. The current is negative current because of the current is flowing out of the input circuit and it is going into the input circuit. So that's why here the IIL is, it is in of the milliampere. And for a typical case of the LS TTL NAND gate, if you take LS TTL NAND gate, if you take NAND gate, if you take, the current will be in the order of minus 0.4 milliamperes. So this is a typical value we have considered, or we have considered from the data sheet of the LSTTL. And the second one, what is IIH maximum? What is IIH maximum? And coming to the back, the sinking current here, IIH maximum. So in this case, if you see, so now the output of the TTL gate is in the logic high state. Logic high means 5 volts. The output is in high state. In such conditions, the current flows out of the gate. So when the current is flows out of the gate and which is entering into the TTL input gate. So when the current is flowing into the TTL gate, it is a positive current. It is a positive current. But you see, what will be the current here? The current will be in the order of the microamperes. Why it is microamperes? Because of this high state output, this makes the D1XP diode to reverse bias. So when it is in reverse bias, there will be a microampere range of current will be flowing in the diode. So it is the plus current. And what would be the typical value for LSTTL gate here? So for a LSTTL NAND gate, the typical current value is 20 microampere. Why it is in 20 microampere? Because the TTL input diode is reverse bias. Therefore, the range of current is in the order of the microamperes. In the case of IIL maximum, the diode is forward bias. So therefore, the current is milliampere, but it has a negative value because the current flows out of the TTL input. These are the two current parameters. Now, see the other two parameters, IOL maximum and IOH maximum. So to understand these two, we will go to the source current here. We will go to the source current here. So we will go to the source current here. So now take this IOL maximum. IOL maximum. What do you mean of this IOL here? So it is the logic state of the output. So when the output is at logic state 0, when the output is in zero state, so then the current can sink into the output gate. The current will sink into the output gate here. I am telling with respect to the IOL. Okay, IOL. So the current going into the circuit here. So you can easily understand from this diagram. Or so let's say the 0 here, and we are we are seeing the IOL here. IOL. So we are with respect to the output currents. In the before that we have seen the with respect to the input high state and low state currents. So now we are seeing the output current with respect to the high state and low state. So let the output is 0 here. So when the output is 0, the current is flowing into the circuit here. So the current is flowing into the circuit, and the current flowing into the output gate without disturbing the voltage of the voltage of VOL, without the disturbing the voltage of VOL. So that you can see here, the maximum current and output can sink in low state while maintaining the output voltage not more than the VOLs without disturbing the VOL maximum voltage. What is the VOL maximum voltage in TTL gate? The maximum is 0.5 volt. It is 0.5 volt here. So the IOL maximum volt current, it should not affect on the 0.5 volt here. The voltage must be a 0.5 volt and the current is the maximum rating current. At this voltage, the maximum current flowing in the circuit. And for a typical value for this LSTTL, this current is 8 milliamperes. Why it is 8 milliamperes? Because the current is going into the circuit which is coming out of the TTL input here, which is coming out of the TTL. Because of this low state value, it again causes the D1XP forward bias. When it is forward bias, the current flowing out of the circuit, and here it is into the circuit. So but we are not taking it as a negative value here, because we are with respect to the output currents. In the previous one, we are with respect to the input current. That's why the current is going away of the circuit. That's why we have taken it as a negative value. But it is the case of the output. So the IOL, that is the current going into the output gate. So the current going into the output state is the current of the milliampere current, because the diode is forward bias because of this low state. And the typical value for that is 8 milliamperes. Similarly, the next case is IOH maximum. So in the IOH maximum, so here assume the output at high state. When the output is at high state and with respect to the output current IOH, it is the maximum output current when the output at high state. So in that case, the current is going out of the output gate. So when the current is going out of the gate circuit, it is a negative current, and because of this high state, the diode is in reverse bias. So therefore, the current will be in microampere range. So the typical value for a LSTTL is 400 microamperes here. 400 microamperes. So these are the 4 current parameters, and all these will be supplied by the manufacturer only by looking at the data sheet of the corresponding logic gate. So we can come to know the maximum rating of these current values here. Once if you take these values from the data sheet or the specifications of the gate, so then we can measure the DC output of the TTL gate. So we will see that the DC output. Let's see here. So for a typical LSTTL, for a low power Schottky transistor logic NAND gate, take NAND gate. So for that TTL NAND gate, LSTTL NAND gate, these are the ratings, these are the rated values given by the manufacturers. So now the IAL maximum, IIX maximum, IOL maximum and IOX maximum. If you know these values, you can find out the low state fan out and the high state fan out here. What is a low state fan out? The low state fan out is the maximum number of gate inputs that can be driven by the gate output during the low state output. And the high state fan out is the maximum number of gate inputs can be driven by the single gate output when the output is in the high state value. So first we will see the low state fan out. So the low state fan out is the ratio of the IOL maximum, IIL maximum. IOL maximum and IOL maximum. So now if you take the ratio of this, so it is giving a value 20 here. The value is 20, which means that the LSTTL NAND gate during the low state output, it can handle maximum 20 of the TTL input gates. 20 TTL input gates. And take the second one, high output, high state fan output. So in this high state fan output, it is the ratio of the IOX maximum, IOH maximum to the IIH maximum here, IIH maximum. So now this value, it is giving the value 20 here. So which means that the low state fan out is the DC fan out 20. During the high state, the DC fan out is 20. So therefore, now the fan out of the given TTL gate is 20 here. But it is not the case to, but it is not common to all the cases. For some TTL gates, the low state fan out may be, some cases it may be 10 or it may be a 5. And the fan out high state value may be a 20 or a 10 value. If the two low state fan out and the high state fan outs are equal, then the DC fan out of to that corresponding gate is 20, say in this case. But if the low state fan out and high state fan out are the two different values, then the overall fan out is the lower value of the between the two fan outs here. So here the lower value, the lesser value of the two fan outs, whichever is the lesser, that is the DC fan out. So during the low state, it is driving the 10 TTL inputs. During the high state, it is driving the 20 TTL inputs. But if you have connected excess TTL inputs in the low state, that will leads to the improper operation of the circuit. So that will result into the abnormal operation here. So it will not give us the expected outputs here. So whichever the fan or lower output, so that will be the overall fan out of that DC fan out of to that gate here. So why we need this fan out here? By knowing the information, by knowing the value of the DC fan out only, we can connect the maximum number of gate inputs to that single gate output. If you connect excess gates, if you connect excess gate inputs to that single gate output, the operation will be deviated to the normal values. From the normal values, the operation will be deviated. So it results in increasing the transition times. It increases the propagation delay, which results in decreasing the speed, and also the voltage parameter values will be changed here. Once if the voltages will be changed, so the output or the circuit will not be functioning properly here. So therefore the fan out is one of the desirable characteristic. Knowing the value of characteristic, knowing the DC value only, we can connect the maximum gate inputs to a single gate output here. Even it is the case of the fan in also. Okay, so this is the fan out. So simply for the fan out is the measure that the number of gate inputs that can be handled by the single gate output. And the DC fan out is very important to any logic gate, and the DC fan out can be determined by 4 current parameters: IIH, IIL, IOH, IOL maximum rating currents. If you know the maximum rating of the currents, then you can determine the low state fan out, you can determine the high state fan out, so that you can know the DC fan out. According to that, you can connect the TTL inputs to your gate. So this is about the fan out. So this is about the fan out, and the next gate is, and the next parameter is unused inputs. Unused inputs. So in the CMOS logic, the unused inputs are tied to the used pins, or the unused pins in the CMOS, they are tied to the pull up and pull down networks, to the VCC or to the ground. So likewise, in TTL logic also, the unused inputs may be tied to the used pins, or the unused pins may be pulled to the high or to low values here. I mean that you can connect to the a pull-up resistor through the VDD, or a pull-down resistor to the ground, so that we can effectively use the circuit here. So if you are not connect the unused inputs, if any pin is left open, if any pin is left open, that results in improper operation again. So that results in that shows an effect on the propagation delay, transition times, and also the voltage parameter values. So the fan in, fan out, unused inputs, these are all very desirable inputs for any logic family. So they will have an effect on the circuit operation if the rating is excessed. So here, the unused inputs in TTL logic, they may be tied to the used pins. You can connect it to the some other input. You can tie it to the some other input, used input, or you may be connected to the a pull-up resistor or a pull-down resistor to the VCC and ground respectively. And that again depends on the requirement of the logic function. The requirement of the logic function here. But the problem in unused pins, the problem with the unused pins in the TTL logic is, in the CMOS, there were no much problems with the unused pins. But in TTL, so the resistance value, so I mean that this compensation resistance values, the resistance value of a pull-up resistor and the pull-down resistors is more critical with the gates than the CMOS gates here. So selecting the gate, selecting or taking the resistors for the pull up and pull down is more critical in TTL than the CMOS here. In CMOS we can easily do that one, but in TTL it must be very careful to take the values of pull up resistor and pull down resistor. Why? Because it is because of the TTL inputs draws the significant amount of the current here, and especially during the low state, if you observe the in the previous point, when the output is at logic 0, when the output is at logic 0, it draws the significant amount of current in the order of the milliamperes. Remember that, milliamperes, because of the diode is in forward bias. So that's why there is a large amount of current flowing in the circuit in the range of milliamperes. So here in TTL, the resistor values have to be carefully choose such that we can have a faithful operation here. So here take the two cases here. One is with the pull-up resistor case, and another one is pull-down resistor case. Pull-down resistor case here. So here, when you consider in a circuit here for the pull-down resistor for the TTL inputs, so you have a unused pins here. You have a unused pins. So these inputs are connected to some other gate inputs or some other logic inputs, say. Okay. So now the unused inputs are these things. In the arrow direction, they have represented the current. So these unused inputs are connected to a pull-down resistor. And what is the maximum value in the TTL VOH under the low state value? What is the maximum value of VOL in the TTL? It is 0.5 volts here, isn't it? It is 0.5 volts, the VOL. So therefore here, uh, therefore here the resistor which you connected here, is a current flowing in that, and that current will not be effect on this 0.5 volts here. It will not be effect on the VOL maximum voltage 0.5 volt here. So such that we have to take a resistor value. So here, if the resistors drives the N, here also we are taking the same LS-TTL inputs case. So for this N number of LS-TTL inputs, then we must have this equation or this relation here. See, where this N represents the number of unused pins, and this 0.4 milliampere is from the data sheet here. From the data sheet, the IIL maximum value is 0.4 milliampere. It is the maximum rated current by the manufacturer. So now the N into 0.4 milliampere into the pull down resistor value, and this value, it must be less than the 0.5 volts. If it is greater than the 0.5 volts, it will not be recognized as a logic 0. It will not be recognized as a logic 0. So now, what is the pull down resistor for this case here? So for example, take the N, the unused inputs, for example, take the 10. So there are 10 unused inputs, and to control the 10 unused inputs, what is the pull down resistor value that is to be connected here? So that you can determine from this here. See, from this relation, you can find the value of RD. The RD value must be less than the 0.5 according to the Ohm's law. R equal to V by I, voltage and the current. The current is 10 number of into 0.4 maximum current. So that is giving the 125 ohms of resistor. So it is a very low resistor value. So by connecting of this 125 resistor value, you can connect, you can control 10 unused inputs of the LS-TTL. So that is this one. And the second one, if you see, pull-up resistor. In the pull-up resistor, the output value usually maintaining at the high state values here. So under such conditions, again here, if the resistor values N LS-TTL inputs, then so we will have this relation here, N into 20 microamperes pull down resistor. So what is this 20 microamperes? It is the maximum rated current of the IIH here. Under such conditions, the diode is in reverse bias. So the maximum rated current given by the manufacturer is 20 microamperes. So for LS-TTL gate. So now, so now for example, here you take the 10 unused inputs, and we wanted to drive these 10 unused inputs when the output is at the logic high state. So when the output is at logic high state and we wanted to drive the 10 unused inputs, then we will connect, then we will connect a pull-up resistor here. Then we will connect a pull-up resistor here. So the pull-up resistor value, it must be less than the 11.5 kilo ohms here. If you take the resistor value greater than this 11.5 kilo ohms, higher than this value, the operation will be leads to unfaithful operation. Okay, so this value must be less than the 11.5 with respect to the current rating value. So in this way, you can handle the unused inputs here. You can handle the unused inputs here. So if you want to handle the 20 number of unused inputs, then the value would increase somewhat higher value, or it will be increased to somewhat high value here. And in the pull down case, the value will be in the pull down case. Sorry, here it is pull up resistor. It is not pull down, it is pull up resistor, because if it is pulling to the high state of value, pull up resistor. But in the pull down resistor, in the pull down case, this one, in the pull down case, you see here in the pull down case, the value is going on low here. It is going down to the low values here. So there should be a trade-off. There should be a compromise. So that will be done by the manufacturers, and they will give us the maximum rated currents, keeping in these values. Okay, so this is about the unused inputs. These are all the examples that we have considered. Okay, so till now we discussed the DC logic characteristics or the DC logic values and the DC noise margins and the fan out and the unused inputs. So with this, we conclude for the BJT characteristics. Of course, there are the other characteristics which are all similar to that of the CMOS logic only, but these are the main characteristics that affects on the TTL operation. DC logic and the noise margin levels, fan in, fan out, and the unused inputs. So these have a more effect on the TTL operation. So that's why we have discussed these as the characteristics of the TTL or BJT bipolar logic family. So this is all about the characteristics of bipolar logic. And I will take the 2 more minutes here for CMOS logic families. We have seen the TTL logic families. So do you remember the TTL logic families? The original TTL logic family is 7-4 series, and after that we have the 7-4L, 7-4S, and after that 7-4L and 7-4H, and after that we have the Schottky 7-4LS, and then 7-4LS low power Schottky, and then 7-4AS advanced Schottky, and then 7-4ALS advanced low power Schottky. These are all the various TTL logic families that we have seen in our previous session. And here the next one is CMOS logic families. So now what are the various CMOS logic families are available? So here the first commercially CMOS logic family is 4000 series. It is 4000 series. It is 4000 series here. 4000 series. So this was the first CMOS series, and this 4000 series offers the very low power dissipation. It offers the this offers the low power dissipation, but it is very slow device compared to the TTL here. And also they were not compatible with the TTL logic families here, because till that time the most widely used are the TTL logic families. After the TTL logic families, they have introduced the CMOS logic. So till that the TTL is most widely common used, and the CMOS is not compatible with that widely used TTL gates here. So this is the first commercial CMOS series here, 4000 series. And later they have a part of number identified with the 7-4 series, similar to that of TTL logic. In CMOS also we have 7-4 series. 7-4 series. So it is the part of number to identify the all CMOS devices. And here this 7-4 series is identified with the 7-4 FAM NN. So where the FAM, it says that alphabetic family mnemonic here. Alphabetic family mnemonic, where the NN represents the numeric function generator. It is the numeric function generator. So that will help us to find out the various logic circuits here. So here the various CMOS logic families are, after the 4000, they have introduced the HC and HCT here. High-speed CMOS, TTL compatible. What is the difference between these two is, high-speed CMOS devices. So which means that a CMOS gate output can drive the CMOS gate inputs effectively here. It is the compatible with the CMOS devices only. Whereas the high-speed CMOS with the TTL compatible, the output of the CMOS is compatible with the TTL gate, so that the CMOS output can drive the TTL inputs here. High speed CMOS TTL compatible, and uh, compatible here. And then after we have this VHC and VHCT, very high speed CMOS and very high speed CMOS TTL compatible. The difference between the HC, HCT, VHC, VHCT are the speed of this VHC, VHCT are as twice as the HC. So they are twice than the HC, HT here, with better output driving capabilities, with better driving output capabilities here. So the VHC is only for the CMOS gates. The VHCT is for the driving the TTL input gates. And after that VHC, so they were released in early 1990s here. These are all 1980s and before the early of the 1990s. And in 1990s, in that duration, so they have released this FCT and FCCT. Here also the same one, the fast CMOS TTL compatible, fast CMOS TTL compatible with VOH. So it is mainly for to compatible with the TTL, not for the CMOS to CMOS. Anyhow, the CMOS gates will be easily compatible because of the low output impedance and low currents. But where to interfacing of a TTL input gate to the CMOS output, it is very somewhat tough job here, because the characteristics are different, the electrical characteristics are different. So that's why they have released, one way you can say that it is an advanced version than the HC VHC. The fast CMOS TTL compatible, fast CMOS TTL compatible with VOH. So here the fast CMOS TTL compatible is twice than the high speed VHC, and better output driving capability with the low power consumption. But the difference is this fast CMOS, it is producing the 5 volts of the high voltage here. That is the drawback with the fast CMOS TTL compatible. Actually the TTL requires only a 3 volts or 2.5 volts is more than enough. But the fast CMOS is producing the 5 volts of the output. As it is producing a 5 volts of output, that leads to the power consumption, that leads to the more power consumption here. So then they have released this fast CMOS TTL compatible with VOH. So which means that the output will be somewhat 3 volts here. Okay, so these are all the CMOS logic families here. You can understand the HC and VHC also here. You can understand the HC, VHC. The HC is compatible with the CMOS devices. HCT is compatible with the TTL. You can see the voltage levels are exactly, or they are identical with the TTL logic families, HCT. But the HC is having the logical values of the CMOS. Okay, these are the voltage logic levels for HC and HCT TTL compatible. And here you can see the TTL, the overall TTL logic versus CMOS logic families. So whatever we have seen in the before classes and this class, so these are all overall available logic families in TTL and in CMOS logic. Okay, and why we are touching this point is, why we are seeing this is, when we are going for interfacing of CMOS and TTL gates, you are supposed to know about what are the logic families are available in the each TTL and CMOS logic. Okay, so these are all the various TTL logic families. These are all various TTL logic families, and these are all the various CMOS logic families here. You can also see the examples here, some of the example with respect to the NAND gate, the CMOS 74 series and TTL 74 series, and they will be differentiated with the alphanumeric code. That's what I said, FAM, this one, see, FAM NM. So the FAM, the alphanumeric mnemonic represents the type of logic family, and the last two numbers mnemonic function designator, it represents the type of gate here, whether it is an and or the other gates in the that logic. So this is for the different logic families here. So we will stop here for today, and in the next class we will discuss about the CMOS TTL interfacing. So for interfacing of CMOS and TTL interfacing, you are know the some knowledge, you should have some knowledge on these logic families here and their logic values. So do you have any questions? So if you have any questions, you can ask me.